Intuitive understanding of similarity. Welcome, everyone. Today, we are beginning a new topic, the intuitive understanding of similarity. Now, before we dive into the formal proofs, let's start with an introduction to what this concept actually represents. In our everyday language, we use the word similar quite loosely to describe anything that looks alike or shares a few common traits, like saying two people have similar personalities. However, as we move into the world of mathematics, and specifically within the study of geometry, we need to be much more careful. In this subject, the term similarity carries a very precise and strict meaning. At its most fundamental level, when we say two geometric figures are similar, we are saying they possess the exact same shape, even if they differ in their size. Think of it this way. One figure is essentially just a scaled-up or a scaled-down version of the other. As we move through the next few slides, we will explore how to distinguish between shape and size, and I'll show you some real-world examples to make this concept crystal clear. The core concept, shape versus size. Now that we've established that similarity is about things looking alike, let's dive a bit deeper into the core concept. To truly grasp similarity, we need to make a very important distinction between two things: the shape of an object and its size. First, let's look at shape. In geometry, the shape of a figure isn't just a vague feeling. It is strictly determined by two things: the proportions of its sides and its internal angles. Think of it this way. If the angles and the ratios between the sides remain unchanged, the figure will look exactly the same to your eyes, regardless of whether it is tiny or massive. On the other hand, we have size. This refers to the actual physical measurements of the figure, things like its length, its width, or its total area. While the shape stays constant, the size is what changes when we scale a figure up or down. So, putting this all together, we arrive at our intuitive definition. Two geometric figures are considered similar if they are identical in shape, even if they are not necessarily the same in size. As we will see in the next slide, a great way to visualize this is by thinking about how we use digital zoom on our smartphones. Real-world example, digital zooming. Now that we have established the theoretical difference between shape and size, let's move away from abstract definitions and look at something you use every single day. To give you a real-world intuition for similarity, I want you to think about the zoom feature on your smartphone camera or when you're looking at a photo on a computer screen. Let's break this down step by step so you can be able to see the math in action. First, imagine you are looking at an original image, perhaps a photograph of a tall building. In this original photo, the building has a very specific height and a specific width. Next, imagine you perform that familiar pinch-to-zoom gesture on your screen. As you zoom in, the image of the building becomes much larger, occupying a much greater area of your display. Now, here is the crucial observation. Even though the size has increased, does the building look stretched or distorted? No, it doesn't. The windows remain perfect rectangles, and the angle of the roof stays exactly the same as it was in the original photo. The proportions haven't changed, only the scale has. Therefore, we can reach a mathematical conclusion. The original image and the zoomed-in image are, in fact, similar. This is because the fundamental shape is preserved, even though the size has undergone a change. This concept of preserving shape while altering scale is exactly what we will see applied to more complex geometric figures, like circles and squares, in our next slide. Figures that are always similar. You'll see that some geometric figures are so strictly defined by their properties that any two figures of that specific type will always be similar, no matter how large or small they are. Let's start with the simplest one, all circles. Think about what makes a circle a circle. Every single circle is defined by just one parameter, its radius, which we can call r. Whether you are looking at a tiny circle with a radius of 1 centimeter or a massive circle with a radius of 100 kilometers, that fundamental roundness never changes. Because the shape is preserved perfectly, all circles are inherently similar to one another. Next, let's look at squares. A square is defined by very specific rules. It must have 4 equal sides and 4 angles, each measuring 90 degrees. If you have a small square with a side length of S1 and a much larger square with a side length of S2, the internal angles are still exactly 90 degrees, and the ratio of their sides remains 1:1. Because the proportions and angles are identical, all squares are always similar. Finally, let's consider equilateral triangles. Just like the others, these are defined by their properties. An equilateral triangle must have 3 equal sides and 3 equal angles. In any equilateral triangle, regardless of its size, every internal angle is always 60 degrees. Since the angles are always the same, and the sides always maintain that same 1:1 ratio, any 2 equilateral triangles you encounter will be similar. Now that we have a good intuitive grasp of what similarity means through our digital Zoom example, let's look at some fascinating cases where similarity is actually guaranteed. As we move into our next slide, we will summarize these key takeaways to ensure you have the core concept locked in. Key takeaways. All right, let's take a moment to recap everything we have covered in this lesson so far to ensure the core concepts are clear. First and foremost, remember our primary definition. Similarity simply means having the exact same shape, even if the size is not the same. As we discussed with the digital Zoom example earlier, you can think of a similar figure as being either a magnified or a reduced version of the original. The proportions and angles stay perfectly intact, only the scale changes. Finally, keep in mind that some geometric shapes are inherently similar to one another by their very nature. Because their defining properties never change, all circles are always similar, all squares are always similar, and all equilateral triangles are always similar, regardless of how large or small they are. Now, before we move on, I want to highlight a very common pitfall that students often encounter, so please pay close attention to the next slide. Common mistakes to avoid. First, let's address the confusion between similarity and congruence. This is perhaps the most frequent mistake beginners make. To keep them straight, think of it this way. Congruent figures are like identical twins. They must have the exact same shape and the exact same size. They are perfect carbon copies of one another. Similar figures, on the other hand, are more like a photograph and its enlargement. They share the same shape, but they can be different sizes. So, while all congruent figures are technically similar, not all similar figures are congruent. Secondly, be careful not to fall into the trap of assuming that if 2 figures look similar, they must be mathematically similar. In our daily lives, we use the word similar very loosely, but in geometry, looking similar is simply not enough. While we have spent today focusing on the intuitive, visual understanding of these shapes, please keep in mind that as we progress in this course, we will move beyond just visual impressions. We will soon learn the strict mathematical conditions required to prove similarity, specifically looking at whether the corresponding angles are equal and whether the ratios of the side lengths are perfectly proportional. Now, before we wrap up today's lesson, I want to touch on some common pitfalls. It is very easy to trip up on a few specific points when you are first learning these concepts. Keep these distinctions in mind as you review your notes, and I will see you in our next session where we will dive into the formal proofs.